When comparing algorithms in terms of efficiency, we use what's known as BigO notation, also known as asymptotic analysis, but BigO for short. BigO is a way of labeling or grouping algorithms according to their relative complexity classes. These are rough measures of the order of magnitude differences. So as problems get larger, as the problem sizes get larger and larger, we're concerned with very big differences in the runtime complexity of these algorithms. So the notation for BigO is just the big letter O, hence the name, and then in parentheses we describe the number of basic operations in terms of the problem size. So if our problem size is n, we have n items to search through, then a linear search, for example, is BigO of n, because in the worst case it has to check every single item. Now the O here stands for order, as in orders of magnitude, and the class here is how much work the algorithm will do. And if an algorithm has a BigO of order n, that means that as the problem size grows, the complexity of our algorithm will grow linearly with n. So if we have a list that's twice as big, we'll have to do twice as many comparisons. If the list is 10 times as big, we'll have to do 10 times as much work. This also means if we can find another search algorithm that runs in order n time, we can say it's approximately as efficient as a linear search. And we say this even if there are small differences in constant factors that separate these two things. So for example, if we had some search algorithm that did 2 comparisons for every item, for a total of 2 times n comparisons in the worst case, we would still consider that to be BigO of n. That is to say, we would consider it in the same class of magnitude as a linear search, which is O of n. This is because if the problem size were to double, both of these algorithms would only double the amount of work they had to do. To develop an intuition on this, let's see this in Excel. So let's create a column here. We'll call it n, and it will have the numbers growing in a linear sequence. So 1, 2, 3, 4, 5, 6. And I'll just take all of this and autocomplete down to around 50. Okay, so now we have all the numbers from 1 to 50. Now I'm going to create another column here. This is going to be 2n. And this is just going to be all the values times 2. So equals a2 times 2. And as we expand, we go from 2 all the way to 100. So let's graph these lines in a chart here and see what they look like. View, nope. Insert a line chart. So here's an example of the 2 lines. So blue is our n, and orange is our 2n. And notice the difference is getting bigger as our problem size is getting bigger, but it's getting bigger by a constant factor. It's always twice as big. So BigO notation calls these both O of n because they're not orders of magnitude greater than one another. To make it clear why this is because some algorithms are far worse than twice as slow. For example, let's make an n squared column. So this is a2 times a2, so a number times itself. And we'll do all 50 of those as well. And then let's add this to the graph. So we'll say select data, and we'll just select all of these. Now we have 3 lines here. Let's just make this a bit bigger so we can see. And notice the n and the 2n lines have been squished down to the bottom here, almost to the same flat line, in order to make space to depict the rate of growth of n squared. So n squared grows much faster as the size of our problem grows. So if our problem size is represented by this column n, then a problem that's growing linearly with n, like a linear search that has to check every single item. So if we double the items, if we go from having 25 items to having 50 items, we're just doubling the amount of work. The same is true in 2n. If we go from having 25 items and doing 50 steps of work, if we double the size of our input, we're doubling the amount of work we have to do. But if we consider the n squared column, if our input size is 25, we're doing 625, let's say, comparisons. If our problem size doubles, the amount of comparisons we have to do, in this case, is over 2,000. So when our input size doubles, the amount of work goes up by a factor that's larger than 2x. So 2,500 over 625 equals 4, because 4 is 2 squared. But importantly, notice the factor itself is increasing as the problem gets larger. If our problem size were to triple, then n squared goes up by a factor of 9 times more work, because 3 squared equals 9. This is an example of the different orders of complexity. In this case, order n, which grows linearly, versus order n squared, which grows quadratically. So in terms of the large differences in runtime between different algorithms, BigO distinguishes several specific classes, and we give names to each of those. The first class is known as constant time, or O of 1, and these are for algorithms or operations that do a fixed amount of work. So these are basic operations like an assignment operator or a comparison, or an algorithm that finds the first item in a list. Now, a linear time algorithm, the work increases linearly with the problem size. We've seen at least one example with the linear search. So any sort of traversal of a list where we're doing a constant amount of work with each item is going to result in a linear amount of work for the entire list. Now, if our size doubles, then the algorithm's work has to double. A third class, which we haven't yet seen an algorithm for, is known as the quadratic time algorithms. And these are algorithms that run in order n squared. So in this case, the work increases much faster than the problem size. If the problem size doubles, the algorithm's work goes up by a factor of 4. If our input size triples, then the algorithm's work goes up by 9 times. If n goes up by 10 times, then a quadratic algorithm's work goes up by 100 times. There are other classes that we'll see, but let's just see some examples of these first. So returning to VS Code, let's make a new file. We'll call it bigo.py. And I'll just do a quick demonstration of a few of these classes. Starting with a constant time algorithm. So if we have some problem size, we'll say n equals 100. A constant time algorithm would be something like print n. This is an order 1 algorithm. If our entire problem was just print the size of our problem, generally speaking, it takes a constant time to print that value out. It's worth also noting that if an algorithm takes 2 steps or 3 steps or 1,000 steps, as long as it's a constant number of steps, it's still considered O of 1. So for example, if I were to say print n and then print n, our algorithm now has to do 3 of these basic operations. But now notice, if I make our n 10 times bigger, we're still doing exactly 3 operations. So it's not going to change the amount of time it takes if our problem size increases. In all such cases, we say the algorithm runs in constant time. Next up is the linear class of algorithms. And as I mentioned, this shows up anytime we do a traversal or a repetition that's linear with the size of our problem. So for example, if I said for I in range n, so I'm doing a loop from 0 up to n. If n doubles, that loop is going to double the number of repetitions it has to do. So we'd say this is O of n times the cost of whatever operations happen inside that loop. So in this case, let's just say, I said print n again, which we saw was an order 1 operation. So n times 1 equals n, so this loop gives us order n total. Notice, if our problem size doubled, we'd have to do twice as many repetitions, we'd have twice as many print statements, so that's twice as much work. If our problem size went up by a factor of 10, we'd have to do 10 times more print statements, so 10 times more work. As an example of a quadratic class algorithm, we could say, for example, for I in range n, which is again just a linear loop, but then the action taken inside of that loop could itself, for j in range n, repeat another n times. So this is also O of n. Now if we have O of n times whatever is inside this loop, which is also O of n, times, and then let's say we have a constant operation in there like print n, or even just print I times j, or something like that. This is still a constant time operation, so we have n times 1, which gives us n squared. Now notice if our input n here were to double in size, the outer loop would have to do twice as many repetitions, and for each one of those, it would have an inner loop that also has gone up twice the size. So we're not increasing linearly with the size of n, we're increasing quadratically. We have that n squared curve, which leads to a lot more work with small changes in our input size. So let's label all these. So this is a constant time algorithm. Say this is a linear time algorithm. We say this is a quadratic time algorithm, which is n squared. N and 1. Okay. Let's see one other class of algorithm here called the logarithmic time algorithm. Logarithmic, which is O of log of n. So for example, if I had a loop, I said I equals 0, and I said, while I is less than n, we'll do some work like print I, for example. But then instead of increasing I by a single value, instead of saying I equals I plus 1, I'm going to say I equals I times 2. So if I starts at 0 and then, start at 1 then. So if I starts at 1 and multiplies by 2 each time through the loop, then what happens, if our problem size doubled, this would only take a single extra step. So it's not going to take twice as much work to manage a loop that's twice as big. It's going to take a little bit more work, but less than linear. The curve of log n increases, but it does so at a rate that's less than linear. So in a logarithmic time algorithm, the work still increases as our problem size increases, but by less than a linear amount. So the big O of log n is somewhere between O of n and O of 1. So this is the idea behind BigO notation. We can take algorithms of various different forms and factors, reduce the analysis down to just the core operations, and consider the runtime of those algorithms in their worst case relative to the size of their inputs. Then we can use those counts to either compare or group these algorithms according to the orders of magnitudes of difference in their complexity. That is, the amount of work that they will do relative to some input size.